As part of my research this year, I worked on testing the holding structure for the DAMIC-M charge-coupled devices, which are designed to find dark matter particles. Finding such particles would resolve one of the greatest current mysteries in physics, the dark matter problem, which tells us that there is more mass in a galaxy than that which we can see. We can tell this via the graph on the left, where the line labeled a disk displays predicted gravitational effects in a galaxy. The upper line displays the observed gravitational effects, and so the difference, which is labeled halo, we think must be explained by some unknown particle which does not interact electromagnetically, thus being called dark matter. DAMIC's approach to finding this particle is by using charge-coupled devices, which are capable of taking very precise charge measurements. If a dark matter particle of a certain size were to pass through the detector, it would dislodge charge, which we could measure. To run this device, there must be very low background radiation. So the holding structure must be made of highly radiopure electroformed copper, which must be grown in a cylinder. After being grown, it is bent into plates and machined into trays, which hold the detectors, which are then placed deep in a mountain in the Alps to avoid radiation from space. The problem I was tasked with solving is that the detector must be run at very low temperatures, but some were worried that these temperatures would cause the copper to warp back into its original cylindrical shape. Any more than 150 microns of warping would harm the CCD. We were fairly confident that there would be no warping, but we wanted to be sure, as breaking a CCD could be very expensive for the experiment. The first tests I ran used a laser scanner to take profile measurements of the tray. I took one measurement before cooling the tray in liquid nitrogen and one after, then compared the measurements. I found that there was no significant warping, and any warping that was seen was not around the axis which we had worried about. However, there was interest in seeing measurements taken while the tray was cold as well. To do this, I used a dial indicator with an extended probe and an insulated containment box for the tray, taking measurements while warm and while cold, and then comparing them. Initially, the measurements seemed to be different, but it turned out that this is because there was tilting on the stage caused by warping of the containment box. Trend correcting the data allowed us to see that there was no noticeable difference between warm and cold measurements, as we can see on the bottom right. This means that the tray should be good for use in the experiment. However, further work should be done on newly fabricated trays, as the work I did was only on one test tray. But that should not be too tough, as a solid procedure has now been developed for testing the warping of trays.